Okay, so last time, I think we just barely scratched the surface on this one. We talked about some of the terminology and what it means, but let me just go ahead and repeat that just in case. So we have here this curve, which goes like that, and this curve, of course, which goes like that. The domain given here, D, is what we call bounded by these two curves. And again, this is special terminology. This means more than just that the boundary of the given region is these two curves. It has to mean more than that because this, for example, is a subset of the plane whose boundary is, in fact, just those two curves, right? So this is not a sufficient concept. We further require, when we say the term bounded by, that the region is bounded, that you can put a fence around it, that you can fit it inside of a box, however you want to say it. It doesn't extend infinitely in any direction. And so there is only one region that meets that more strict criteria, those more strict criteria, that's this region right here. So heads up, just do be careful. This is part of the question, is to interpret the question correctly. So make sure to think carefully when you see this term bounded by. Okay. Now, with that said, how are we going to do an iterated integral on this region? We've got a couple different options for how we can do the differentials, either dy dx or dx dy. Now, arbitrarily, I'm going to start with doing dy dx. Let's think about the range of values of x. The x slices, of course, there's the x direction. X slices, therefore, look like this. Right? And we can see that they start at that point. Right there. Now, remember the process, the general process is you identify the point that gives you the bound you're looking for. Identify that point as being on certain curves. Those curves have certain equations. And then you solve for what you need. So, okay, well, this point here is on that curve with that equation. It is also on that curve with that equation. And so, within this pair of equations, I need to solve, and let's see here, what am I doing? Apparently I'm solving for x. I'm looking for an x bound. So, within this pair of equations, I need to solve for x. And notice, you can't just, well, there's the number, I see the 4 right there, and just declare 4 to be the answer, right? Of course, you have to literally actually solve. In this case, if that's what you're solving for, its square is y is 4, therefore its square is 4, and so we're talking about plus or minus 2. And then I look over here and notice that my lower bound that I'm looking for is negative, and because it's negative, it must be minus 2. Everybody happy with that? Notice, again, there were two options. You have to recognize both of the two options, and then the geometry of the picture or some indication from the diagram itself will allow you to clarify which of those options. Okay. All right, likewise for the upper bound. Now let's fix a value of x. Fixing a value of x somewhere between negative 2 and 2. Now, as we do our y bounds, we're entirely confined to that x slice, and process begins again. Okay, so how am I going to find the lower y bound? Well, okay, the lower y bound comes from this point. This point is on that curve, which has that equation. Oh, wait a minute. What am I solving for again here? It's easy to lose track. I'm looking for a bound on y. So in this equation up here, I need to solve for y. Good news, it's already solved for. It's x squared. A little bit concerning that it doesn't feel like we solved. It feels like there's a variable there. But don't forget, x is the outside variable, and being the outside variable, it is to be taken as constant for the purposes of the inside integral. And so this expression, x squared, just some number as far as this integral is concerned. So that y is solved for. Okay, upper bound. How am I going to find the upper bound here? Again, keep in mind, x is fixed. We're confined to this x slice. We are now going to focus on the upper bound. The upper bound comes from that point. That point is on this curve, which has that equation. And again, reminder, I'm solving for y because I'm trying to find a bound for y. And so solving for y. 4. Everybody happy? Questions? Note, what we need to focus on here is the process, right? Not the algebra, the specifics of the algebra. Pretty straightforward. Just make sure you understand that the sequence of connections that we draw to do the algebra. Okay, now we're going to do the same domain, same exact domain, same curves, bounded by all that. This time, differentials in the other order. So, starting with y bounds, y. There's the y-axis. Here's our y slices. And those being our y slices, there's the first one. It's at the origin. Not much needs to be said. If it's at the origin and I want to solve for y, well, y is 0 because it's the origin. Again, sometimes the fish jump in the boat. Good news, take the good ones when you can get them. Next, the last slice up here. And I suppose you could pick one of these points, that one or this one or this one. You could, I suppose, but eventually, of course, we'll be solving for y, and all those points are on this curve for which y is already solved for. So again, sometimes you get some freebies. Good. There's our y bounds. Now, as usual, we fix a value of y. We look at just that y slice. And now we move to the inside variable, this time being x. Okay, so where do our x slices start? Lower bound, that point, on this curve which has that equation. Now again, this is where a lot of students will mess up. A lot of students play a little bit too fast and loose. Oh, there's the equation. I guess I'll just take, the thing and make that my bound. That's not the process. Make sure to follow the process. We are looking for an x bound. So we have to, in this equation, we have to solve for x. And x is not x squared. Right? So solving for x, you're going to get, plus or minus the square root of y. And then we argue that the bound I'm looking for here is clearly negative, and thus negative square root of y. Is everybody with me? Again, a little bit disconcerting that, seems like we have a function in here. Is that okay to have as a function? Yeah, sure, because y is a constant. Outside variables are constant for the purposes of the inside integral. So, no problem. Okay, ditto for the upper bound. Pausing on this one. Everybody feel good about it? Everybody see the little landmine there? Okay. So, we have two options then. For this original integral we were asked to compute. Let me pick a better color. For this integral we were asked to compute, we could do this one, or we can do this one. Take your pick. Doesn't matter. I'll give you the same answer either way. Personally, I have a preference. I like this one better. I'm a little scared of this one. Now let me explain why. Keep in mind, f has not yet revealed itself. I don't know what f is. If f were some sort of an inconvenient function, after I do the x antiderivative of this function, presumably I would have a still worse, more inconvenient function. And then, what am I going to do with that antiderivative? I'm going to plug in these inside bounds. So these inside bounds, whatever they are going to be part of the integrand for your outside integral. And square roots in an integrand, no fun, right? Always a bad thing. Exceptions granted, but almost always a bad thing. So, I am not happy about the way this integral turned out because of those square roots being in the bounds. Okay. So if I had my pick, I would much rather do it this way. Does everybody buy it? All right, so next question. Question. Yeah.
Yeah, I have two questions.
Yep.
What would go in for F?
Yeah, I deliberately left that out. So I don't know. It depends on what the, I don't know, if we're computing mass, then this would be density. If we're computing population, then this would be people per unit area, whatever.
But one of those things where you put like squares everywhere, or you put triangles everywhere, and they have different like area formulas for the total volume.
I'm not following. I'm sorry.
Okay, sorry. It's a calc one thing. My question might make it more clear. Is there like a way to interpret the double integral there?
Yeah, I mean, so, the double integrals in general, right? We write it down when there's some question, some application we're interested in where the quantity is an accumulating quantity, the whole is the sum of the parts, and I break up the entire problem into a bunch of smaller problems that happen on little subrectangles, right? And the integrand is going to be what I call the associated density. It's, if you're computing mass, then the integrand is mass per unit area. Right? But if you're computing population, then it's population per unit area. It depends on the application. So the point is, I didn't want to get distracted by that. That's not what we're doing in this example. In this example, we're talking about how to do step 2. How do I turn double integrals into iterated integrals? Does that make sense?
Yeah.
So, but the point though is that, if this were a real application, then eventually I would have to know what f is. And if f were such that the antiderivative here is a kind of a nasty function, then having square roots stuck into it would make it even nastier. Yeah. Okay, how we doing?
So if we were just computing straight area, would f be 1?
Yes.
Because everything would just be 1 unit.
Yep, because area is 1 times area. Yep, exactly right. Yeah. All right. Okay, cool. So, how can we anticipate which one of these is the good one and which one of these is the bad one without actually having to write them both out? Right? There's a certain amount of effort that goes into finding these bounds. And there's no perfect answer to this question, but there is a lesson that we can learn from this specific example. And I'm going to ask kind of where did that square root come from? The square root came from the fact that I had to solve for x here. Because solving for x in this equation, right, is what led to that square root. Now, why did I have to solve for x here? Well, I had to solve for x because x was on the inside. Right? This example up here worked out more nicely. I didn't have to solve for x. X is on the outside. In this example up here, I had to solve for y because y is on the inside and y is already solved for. Right? So the order of the differentials, there should be some consistency of some sort between which order you put the differentials and which one of the variables is more naturally viewed as a function of the other. And that's not that, you can't invert, you could have it either way, I suppose, but when you have this algebra y equals x squared, a lot more desirable to view y as a function of x than to try to view x as being a function of y. Does that make sense? So, good general rule of thumb, and this is not a law, and exceptions granted, but all else being equal, whichever variable you view as being the input variable, such as x in this case for that equation, right? X being the input variable, it's nice to put that input variable on the outside. Said differently, whichever variable you view as being an an output variable, makes sense to put that on the inside. Everybody happy with that? It's just a strategy. Far more often than not, this will make a good choice for you. Okay. Here's another example. And again, just, kind of doing examples at this point. We've got here a triangle with certain corners given. And there's our corners, so this is our triangle. And how are we going to do an integral on this triangle? Well, again, let's not worry about the application. Consider, phase 2 of the process only. And so we're going to just try to turn a double integral into an iterated integral and leave it at that. Again, I have two choices. Arbitrarily, let's start with dx dy. All right, well, y slicing goes that way. First slice there, last slice there, no problem. Get some easy bounds. Then we fix a value of y somewhere in that given range. And now, to find my lower bound for x, I look at this point, which is on that curve, which has an easy equation to write down, and that lower bound is y. And then for the upper bound, it's this point, which is on that curve, and again, you write down that equation, and you solve for x, and you get that upper bound. So no problem. This went through pretty glass smooth. Fine. Not a particularly interesting example, so it seems. However, let's look at what happens when we slice it the other way. And something kind of bad's going to happen here. All right, here we go. Arbitrarily now doing the x slicing first. X, it would seem, goes from 0 to 2. But there's a problem. Because here's the thing. For these values of x, between 0 and 1, let's just kind of anticipate. Let's, don't worry about the bounds for x. Let's just think just for these values of x between 0 and 1. Let's think about the upper bound for y. The upper bound for y is going to come from this point, which is on that curve, which would give me that upper bound for y. Whereas, for these values of x over here, for x between 1 and 2, for x between 1 and 2, for these blue values of x, notice that my upper bound for y comes from this point, which is on a totally different curve with totally different algebra, and I get, therefore, a totally different upper bound. So this is the problem. If I choose to do my x slicing first, and I'm doing slicing like this perpendicular to the x-axis, my upper bounds are on this purple curve for a little while, and they're on this dark blue curve after that. I have two different equations in which I need to solve for y. And I get two different answers, and you can't have two different answers in your bounds for an integral. You can only have one answer. So because of the fact that our upper bound point, you might say, kind of jumped from this curve to the other curve, and because that jump happened at this corner where x is equal to 1, that's why I have to stop this integral there and start a new integral at that same point. Right. So this is awkward, right? Pretty undesirable answer to have to deal with. Again, you get to choose. I mean, there's either one's technically fine, and if you really do want to work out two integrals instead of one, I suppose you could do that. But it doesn't look as good. This is not. I'm going to say this is not as good of an analysis of the problem. It's analyzing, pointlessly doubling the effort. So it seems, right? So this is a bad answer. This is a good answer. Yes.
Can you explain the bounds on the first one again?
Yeah, sure. So let's see here. Y goes from 0 to 1. Is that all right? Okay. And then, all right, so now we're going to focus on a given fixed value of y. There's my y slice. Now I want to talk about what the x bounds are. The lower bound comes from this point, which is on that curve, which has equation y equals x. I need to solve for x. in the equation y equals x, and I get that x is y. Is that cool? Yeah. Okay. Yeah. And then likewise for the other. Okay, so what's the lesson here? And again, do I have to actually write out both options in advance, and then only then do I decide which one do I like and which one do I not like? No, there's a nice little shortcut. And the shortcut to make this observation is if we look at what happened in this second approach here, as we were doing x slices, the way I like to say it is we sliced through a corner. It is because of the fact that we sliced through a corner that we had to then say, okay, well, yeah, for those values of x, blah, 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 but for all of these values of x that follow between 1 and 2, I've got a totally different deal. Right? So if you don't want that to happen, don't slice through corners mid-process in your outside slicing. Now, just by comparison, look at what we did up here for the first one. Did I slice through any corners? Not really. I mean, you could make the case that y equals 0 slices through a couple of corners, but I was going to start a new integral there anyway. So that's all right. Right? Mid-process, no corners, and then at the end, yeah, the end is a corner. Arguably, I need to stop my integral there, and I don't need to start a new one. I was going to stop there anyway. So again, that corner doesn't matter either. But mid-process, didn't slice through any corners. Everybody happy? All right. So another sort of like, unofficial, this is a strategy. It's a word of the wise. All else being equal, tends to give good advice. Try not to slice through corners. Okay. So remember, think about which variables on the inside and which variables on the outside. You ideally want to put your input variables on the outside. And then secondly, all else being equal, try not to slice through corners. And between the two of them, this will lead you in the, if there is one slicing direction better than the other, this will get you there most of the time. A vast majority. Okay. All right. Just another example. By the way, you'll notice we're just doing a bunch of examples here. I want to sort of walk y'all through representative collection of it, show you various kinds of issues and complications that can come up, just so you can have been there for most of these things. Here, question says to find the volume between these two surfaces. Namely, let's find this volume right here. And what's weird about this question is it doesn't give us a domain. Right? It doesn't say compute the blah, blah, blah over the certain domain, or compute the amount of whatever sitting over a certain domain or sitting on a certain domain. There's just no domain given. Right? So how do we find the domain in a case like this? All right. Well, real quick, first of all, I want to point out that, the way the double integral works out, again, we slice up the volume into vertical slices like this that come from little pieces of area down there like that. And this little piece of volume, French fry, as I like to think of it, you'll notice is a height times a base. The height here, that height is this z-coordinate minus that z-coordinate, so z2 minus z1. That's the height. And then the area of the base, this little area there is that, well, it's whatever this area is down here, which is dA. So forming the double integral is no problem. Again, the issue, the complication, is we're going to figure out what is the domain we're going to pick for this integral. I'm going to show you now the wrong answer. This is a very common mistake lots of students make. So again, I want to show you where the landmines are. Here's one of the landmines. A lot of students will reason as follows. They say, correctly, that they're looking for this curve as a way to understand the domain. This shadow down here, that is our domain for this integral. Where that comes from, they note correctly that it is the projection of this curve up here, and they note correctly that that curve is the intersection of this surface, oh whoops, wrong one, that surface with this surface. This is all good so far, right? Trying to find the purple curve, which is the intersection of these two surfaces. Here's where the mistake is, the landmine. Students say, well, if I want both equations to be true, I'll set the two equations equal to each other. And students will then typically say, all right, I guess I'll set that equal to that. And I claim that's an absolute non sequitur. It doesn't make any sense. And just for the purposes of exaggeration, for emphasis, let me give you a different, sort of more preposterous scenario. Let's suppose you want this equation and this equation both to be true at the same time. Would you require that 3 equals to 6? No, that's ridiculous. Right? Does everybody see what I'm talking about? It just doesn't make any sense to set equations equal to other equations not thing. Is everybody happy with that? I mean, feel free to, if you have any reservations on that. Okay, let me show you what we need to do. Oh, actually, let me, while I'm here, let me just point out another thing. Just picking on this bad approach. Setting this part equal to that part would make about as much sense as setting z equal to 7, which would be, for some reason, we'd be looking at a plane like that for no apparent reason. Right? It just doesn't make any sense. Okay, so what do we do? What am I looking for here? I'm going to zoom so we can see a little bit better. Bet you I can even go one more. There we go. Okay. So notice that what we're actually looking for are certain points down here. Not this one, but at that point, I can look at the value of z that gets me up to this plane. That's my z2. And I can look at the value of z that gets me up to, that gets me up to this surface, right, which is that value. These are different values. Of course they are. We're not on the appropriate edge. What we're looking for is points like this one, where the value of z getting me up to the plane and the value of z getting me up to the paraboloid are the same value. Right? These are the same. That's what defines this curve here, is that the green height and the blue height are equal. All right? Geometrically plausible? So notice, again, there are two things that I want to be equal. I want green to equal to blue, but specifically these z values on these surfaces. It's the z values that need to be equal. So going back to the equations, I'm not going to set this equal to that. That's not a thing. And I'm not going to set one side of the equation equal to one side of the equation either. I've got to look specifically at the z's in these equations. Those are what I want to set equal to each other. I need for z1 to equal to z2. And now you got to do a little bit of work to find those values of z. Z1, let's see, z1's the one on the paraboloid. Z1 is that right there. Right, Z2, if I can get that to erase, Z2, I'm going to have to do some algebra to solve for that Z. This Z2, though, ends up being that. So this is the equation that I need to describe what I'm looking for. Let me zoom in so we can see that better. Everybody with me? Okay, and it's all over but the shouting at this point. So you got this equation, move things around, complete the square. By the way, make sure you're good with completing the square. I know it was a long time ago in algebra class. A lot of students mistakenly inferred from high school algebra, myself included when I was in high school algebra, that, I don't need to learn how to complete the square. The quadratic equation takes care of that for me. I'll just memorize the quadratic equation. Well, that only works if what you're doing with your quadratic is trying to find its roots. That's not what we're doing here, right? So, sadly, no, the quadratic equation does not obviate completing the square. Here you've got to complete the square. Make sure you can do that. Make sure you're all polished up on that skill. And then at the very end, notice we have the equation of a circle, and that is the equation of our domain down here. At least the boundary of the domain. If I can get this stuff to So that right there is that circle. Yes.
That circle looks like it's centered on the origin.
Yeah, it's bad art.
Is it?
Nah, it's no, definitely not. You can see here the center is at -1, -2. It's just
why isn't it centered at the origin if like the
paraboloid is, but the plane's not. So roughly speaking, the point here is that this corner over here is higher, and being a symmetric paraboloid, higher means farther from the origin. Does that make sense? So that side of our circle is farther from the origin, and this being lower means it's closer to the origin, and so it's just offset in. And again, my picture's not to scale, and it's it's hard. So bad art. That's all that is. Yep. Okay. All right, moving along. 5.3 is one of the shortest sections in the book. I think I'm going to spend probably about 5 minutes on this section. It's very quick. Not a lot to say, really. There's one big idea here, and that is if you're trying to compute an iterated integral, for example, this one, let's just, dive right in. Sometimes you run into a problem, such as in this case, trying to compute this inside integral. And again, that's the deal. If you want to compute an iterated integral, you got to start on the inside. Well, I would need to find an antiderivative of e to the x squared, and you can't. Right? There's what we call no closed form antiderivative. What that means, by the way, is yes, you can think back to Calc 2, write a Taylor series for e to the x squared using all those methods from Calc 2. And once you have a Taylor series, then you can take the antiderivative term by term, and you can make that work. It gives you an answer, but it's not in closed form. Namely, it's going to have summations. It's going to have infinitely many terms, and you have to worry about convergence and all that kind of nonsense. Okay, so this is highly, highly undesirable, as written. Okay, so what I'm going to do is just remember that when you have an iterated integral, that iterated integral came from a double integral. This is just one of two options of how to compute a certain double integral. And I'm just going to take this iterated integral and kind of reverse engineer to find what is that underlying double integral. And then I'm going to choose to slice it in the other order. Because I don't like the way this one's working out. This one's got me doing really hard integrals that can't be done. Right, so let's reverse engineer and find what that original double integral is. You can see from the way this is written, y goes from 0 to 1 here. So those are my starting and ending y slices, apparently. Right? And then furthermore, for a given value of y, whatever value of y in between those, for a given value of y, the x lower bound is where x is equal to y, where x is equal to y, which is on that curve, namely giving me that point. There's my lower bound for x. And then let's see here, it says right here that the upper bound for x is 1, which is that curve, which is that curve, which would be that point. Right? So for every value of y between here and there, x goes from that curve to that curve, and said differently, my actual region D is this triangle right there in yellow. Everybody see how that worked? I mean, it's just sort of, working backwards from the given bounds on the iterated interval. Okay. Right, and now that I know my domain, now I'm free to slice it in whatever order I want. Obviously, I don't like the way it worked out when I did the dx dy slice. That led to an impossible integral. I'm not going to do that again. Let's just slice it the other way. Fingers crossed. I hope it works out better doing dy dx. Let's see what happens. Well, x slices look like this. Starting at the origin, ending on this line right there. That makes x go from 0 to 1. Then let's fix a value of x. And let's think now about values of y, and apparently y, according to this picture anyway, y starts at that point, which is on that curve, which has that equation. So y equals 0 is my lower bound. Right? And then let's see here, my last value of y is going to be there at that point, which is on that curve, which is the line y equals x. And so y equals x. Gives me that upper bound. Now all I've done is altogether, I took an iterated integral, I reverse engineered the domain, and then I sliced up that domain in the other direction. And now I've got at a quick glance, seemingly no progress. Now I have a new iterated integral with the exact same integrand, and you'd be forgiven for being frustrated at this point that why is this better, right? And here's the thing: it's like doing a substitution. We do stuff like this because sometimes, unexpectedly perhaps, the new integral just happens to be easier than the original one, right? Just like with substitutions. Same thing here. So this one works out actually really well. This integral is super easy because don't forget, when you're doing the inside integral, the outside variable is a constant. That means x is a constant here. That means e to the x squared is a constant. It's the world's easiest integral, in fact. Integral of a constant. Variable times that constant. Plug in the bounds, subtract, and this integral turns out to be nothing more than that. No problem. Everybody happy? And having done the inside integral, now this outside integral, easy substitution, and it's all over with shouting. So, select move, tool for your toolbox. How often does something like this come up? Here and there, occasionally. It's a nice trick to be aware of. I don't know that it's worth an entire book section for this one trick, but anyway, it's worth talking about. Everybody okay? All right. Okay, so let's proceed now to the next section, 5.4. Let's take stock for just a moment before we get into this. Y'all came into this class fully aware of single variable integrals, and then we briefly entertained the idea of iterated integrals before realizing actually a much better idea is double integrals, right? So we've got single variable integrals, we've got double integrals, and that's pretty much what we've had to this point. Single variable integrals, double integrals. And what's the big difference? The difference is that the single variable integral addresses situations where whatever it is that you're computing is distributed over a one-dimensional interval. Whereas a double integral is what you need if you're talking about quantities that are distributed over an area. Everybody see the difference? Everybody happy with that, right? So just as an example, if you go to the hardware store and buy chain, they will talk about its weight per foot. Right now, is that Is it literally one-dimensional chain? No, of course not. Chains have a thickness to them. They have volume, for sure. It's just that the volume's not how we think of chain. It's not what we do with chain. A chain's job is to have a length. And the width and the depth is almost never relevant for it's not. We're just not interested in that. So we think of it as being distributed across a length. And so you could talk about its mass per unit length. Right? Price per unit length as well. Okay. On the other hand, if you have a two-dimensional region and there's mass distributed across that region, hey, maybe you're growing crops, right? And you've got a bunch of corn out there in the cornfield. You want to know what's the grand total mass of corn that you have in the cornfield. Well, that corn is distributed across an area. And it'd be a lot easier to talk about how much corn there is per square foot. Because yes, technically it also has height, and yes, there's a volume, but we think of it as being distributed across area. Okay. All right, so different kinds of circumstances lead to different kinds of integrals. And the thing is, sometimes mass is distributed across a solid. Not a one-dimensional interval, not a two-dimensional region, but sometimes a solid three-dimensional region. In fact, not only is this sometimes the case, one could argue this is even more often the case. We live in a three-dimensional world. Stuff tends to be three-dimensional. Most of the time we're interested in all three dimensions. And so this is actually arguably the natural way to think of how mass is distributed. Okay, so what we're going to do then is we're just going to develop a three-dimensional version of chop it up, add it up. A three-dimensional version of the whole is the sum of the parts. And so, all right, here's my whole. There we go. There's my solid three-dimensional region. And how much mass is there in that solid three-dimensional region? Well, it's hard to say. The density varies in all the different directions. Too hard. I don't know what to do there. But in a little sub-box, this is very small. It doesn't extend very far in any direction. The density in this little box probably pretty close to constant. Right? We'll take a limit eventually, so these round-off areas will go away, but pretty much we think of this as having close enough constant density. So how much mass is there in this box? Okay, well, whatever my mass per unit volume is, times the volume. Right? This is a three-dimensional version of mass per unit area times area, or mass per unit length times length, just with the understanding that here mass is distributed three-dimensional. All right, now before we actually write down our Riemann sum and get into the taking it from there, we do have to recognize we need detailed formulas. How do I break up and quantify all the details relevant to cutting up an interval on the x-axis into pieces? Old news. We've done that twice already, right? We did it for single variable integrals. We did it for double integrals. What about an interval on the y-axis? How do I chop that up into n pieces? We already have. It's just like with double integrals. So we get to recover all of that from previous efforts. And now all I have to do is think about, I have this interval on the z-axis from E to F. How would I chop that up into n pieces if I'm slicing? Right. And, well, morally equivalent formulas. We take the whole length and divide by n to give us the sort of delta z. And then we successively add delta z's to get us from one sort of point to the next. Just like with the x's, just like with the y's. So this is formalities that just have to get said. We're not actually going to do much, if anything, with that. But I do want it to be clear that we're being very precise when we write this down, and this is what we really are going to do a lot of things with. This is what we mean when we say the whole is the sum of the parts, or chop it up, add it up, whatever you prefer. We're going to take our entire solid region, break it up into little pieces on which we do this calculation. Whatever our application is, I don't know. We don't want to pigeonhole ourselves, right? Whatever the application is, we're going to have quantity per unit volume is what our integral is going to be. We'll multiply quantity per unit volume times volume, which gives us quantity. And then we add up those quantities over the entire solid three-dimensional region. And take a limit for good measure to make those round off errors go away per all of our other integrals we've ever done. So this is a total rip-off of two index Riemann sums, which themselves were a total rip-off of regular single variable one index Riemann sums. And same basic idea then. And this is a great way to solve a very large number of questions. Huge number of questions that very naturally chop up into easy little questions, which you can then add up over the whole. So this is worthy of a name. We call it a triple integral. And I want to be clear that triple integral means Riemann sum. Right? In the same way that all integrals are Riemann sums, as far as we're concerned in this class. And we also have a notation for it, and this is by far the more common thing to write down because it's more compact, it's more convenient. And again, same deal, we write this as dV because it's a shorthand for this thing over here, which literally represents a piece of volume. Right? And this is a shorthand for the limit and the summation. That, of course, is part of every analysis that involves chopping it up and then adding it up. So, it's just notation. Okay, and just like with double integrals, you can get more formal, more rigorous than I am here. And in some situations that's appropriate and even required. We're going to only entertain continuous integrands. Oh, there should be three. There should be three variables there, x, y, and z. Sorry. I'll get that fixed. So for continuous integrands, doesn't matter how you slice, doesn't matter how you partition, doesn't matter which test points you pick. It's all completely irrelevant for those purposes, and so we're not going to worry about it in this class. Okay. All right. So just to repeat what we've already said, if you want to compute a mass over a rectangular box where you know mass per unit volume as a function, well, total mass is the sum of a bunch of little pieces of mass. Notice I'm using the integral shorthand. Technically, what I've written down here, I haven't actually defined. Right? I haven't defined dm. This is just a shorthand, but it means exactly what you think it means. It means I'm taking the entire mass and chopping into little pieces of mass. And each little piece of mass, of course, is mass per unit volume times volume. And then I have literally a triple integral. And then the question is just how do I compute a triple integral? Everybody good? Okay. One little quick warning I want to give, and then we'll call it a day. Y'all have heard me kind of complain about these points of view here. Complain's the wrong word, but I want to de-emphasize these, kind of geometric crutches for thinking about integrals. I believe too many students think about integrals as being area under a curve. Let me say that differently. Too many students rely on this point of view too much. It is a good way to think about single variable integrals. It is useful for a lot of things, but it's not the only way to think about it, and it's certainly not the definition. And I've pushed instead, you'll recall, for thinking about integrals as being representative of adding up things that are actually literally on your domain. So if you have a one-dimensional domain, think of it as the answer to a one-dimensional question. If you have a two-dimensional domain, it's the answer to a two-dimensional question. I like the mass metaphor myself. What's really important about this is notice for a one-dimensional integral, this is a two-dimensional picture. This is only a one-dimensional picture. For a two-dimensional integral, this is a three-dimensional picture. This is only a two-dimensional picture. So when I get to triple integrals, notice if I want to continue this pattern on the left, if I want to think about triple integrals from a sort of a graph point of view, I need a four-dimensional picture. Forget it. You can't do it. This doesn't make any sense. We're not built that way as three-dimensional critters. We just can't do that. Right? So this is yet another reason to think about things from the sort of, chop it up, add it up point of view, which makes perfect sense in all of these contexts. A three-dimensional picture for a triple integral, no problem. Right? As opposed to this graph point of view where you really run into trouble. And then the worst aspect of all of this is that what a lot of students will run into is a lot of students will think about single variable integrals this way, double integrals this way, and triple integrals this way, and then wonder, why do I get a three-dimensional picture for double integrals and a three-dimensional picture for triple integrals? Same picture, why is one two-dimensional integral, why is one three-dimensional? And then they're confused because they're doing apples and oranges, and they have an inconsistent sort of, pattern of intuitions. So, again, I'm not saying that you can't think about things this way. I'm saying make sure that you can also think about this way and always compare apples to apples. Okay, sorry to go a little bit over there. This is a good stopping point. See y'all on Wednesday. Have a good one.